Sure.
Yep.
Are we doing ANSYS today?
No,
Oh,
we do ANSYS every other week, and so we'll do it next week.
Maybe like 8 classes activities in total. Or
For this class, I have, I think 6 that are planned, maybe 7, but it's a little bit less than 540. So 540, I have 8. I have 8 planned for that one.
How's your day so far?
Pretty good. Yeah, Thursdays are a little bit more chill for me because I don't have any office hours.
That's cool.
by the way, Dr. Tran.
Yep.
How would you like to help design a cardiovascular experiment that would be launched up on a rocket?
I think Isaac reached out to me about it. Yeah. I know that there are such experiments out there, but I just have no experience with it. So I mean, I'd be happy to like read papers with you guys and find out, but I can't think of anything off the top of my head.
Yeah, I was thinking about like the main thing I could probably think of would be like some type of, which we already kind of know, but blood flow analysis or whatever, due to G forces, you know, how higher G forces you experience, all the blood leaves your head, you know, goes to your legs, and all that kind of stuff. But yeah, he was thinking about some type of cardiovascular experiment as far as like we're thinking of a just a scientific experiment that might take some notice for the competition. Last year, somebody, I don't know if they won, but they had, oh no, they didn't win, but they had an honorable mention or a second or third place that they were doing anesthesia tests on invertebrates during flight.
Oh, interesting.
It was, yeah.
How did they get all the equipment on there?
I have no idea.
Was it something they actually did, or was it like just theoretical?
Well, so last year's team was, well, the competition was virtual, so nobody really got to watch or do anything like that.
I see.
But it was definitely something that turned heads, and one of the guys who's working on the thing was slightly interested in environmental engineering.
Okay.
And I'm like, do something that has to do with that, you know, atmospheric tests for carbon or some such or whatever, bacteria growth, and I don't know.
That sounds good.
I'm like, do something. Could be something that works, right? But, yeah. If you have any ideas that sound fun or at least halfway interesting, I know my team will love it. We're also attempting to get everybody who has a rocket certified as well. Didn't last year's team did they give you a rocket?
For Finite Elements?
No. Because the rocket team gifted a couple of rockets to people. I know Mayoral was one of them, but I don't know who else they gave it to.
Oh, okay. I did not receive a rocket. That's
No.
for sure.
Well, I'll give you a rocket.
You know, hearing about the G-force experiment reminds me of a really interesting study I heard where I don't remember if it was kidney stones or if it was gallstones, but like people were finding that when they rode the Thunder Mountain ride at Disneyland, that if they had like a kidney stone or a gallstone, it would just feel a lot better after they rode the ride.
Oh,
and
really?
so it turns out that like the exact like vibrations that you experience on that ride is actually perfect for actually passing the stones through your kidney and stuff like that.
Wow.
And so they did an experiment where they put dummies on Thunder Mountain
And they just
they put an artificial gallstone, and then they saw like with decent amount of success, it ended up passing.
That's amazing.
Yeah.
Wow.
Like it seems like a voodoo magic thing. It's like, yeah, ride this ride at Disneyland, you'll feel better. But there was actually some science behind it.
Really?
Yeah.
It's cheaper than going to the doctor.
Yeah.
That's the best.
Oh God, I hope I don't want to experience that. Yeah, at least I have a solution now.
Yeah, my best friend's wife had that problem.
Hmm.
And, he goes, what are you doing? Haven't been able to like track it down other than like a little wave at the CCS. But did you go to the Discover Fest? Either like, we registered, but they didn't have the I guess the pending filled, so we didn't get a virtual day or anything like that. The virtual? I didn't know that. I asked like asking if he was like our president, and he was like, no, we don't have anything because they said everything, yeah, everything is pending, like our registration going through. He's like, I did it. Whatever. I mean, we spoke to you at the, some of us, like, made sure to point out and stuff to the provost came by the shop.
I heard, yeah.
Yeah, she was super excited. And she was like, happy to make sure that we'll got noticed as well. There was a big need there, but we had a few talking about it.
You mentioned every other week we'll be doing
Yeah.
ANSYS work?
Yeah. Yeah.
Next week.
So next Thursday, yes, our next
Oh, right,
activity.
Monday's out.
Mhm.
Yeah, early week, yeah. We're still trying to get our feet under us.
Yeah, we have class Tuesday.
We really?
Tuesday, and next Tuesday, we're gonna be finishing up these lecture notes, and then Thursday, we'll be doing an activity.
Oh,
Yeah.
Yeah.
Forgot.
Yeah, and most of us here are like in Rocker, so there's only a few of us that are in we'll walk on through, and the other team is running, so there's only about like maybe 3 or 4 of us that actually been around these guys a little bit, to kind of know what we're talking about. And just like everybody else is kind of brand new, ready for the same time, but talking about teams, we have pretty good attitude for especially watching you guys, but you know, it's hard. So,
It is, yeah.
I had talked about something or whatever, about, like, we were all, at least I was, they had talked about, potential for sponsorship. We never had it before. And it was like, yeah, and it had to do with like something like communication. Possible GPS or whatever. I was like, our, hey, honest, actually, Chris, they, might send them your way, because I know that Wilbur deals a lot with like radio and comms and stuff, and so maybe they could have like that. I know that like one of the GPS sites we have to use for cars.
Yeah.
Does it really? Yeah, so maybe we can ask the bike, you know, that's what we do but yeah, I was like, oh, I was have fun doing it, but the best way to do it, the last year you struggle with it. And they just didn't know how to do it, or they didn't have to exam, or whatever it was. I don't know what it was. But I know the exams fairly lengthy, but it also requires like a lot of knowledge of the disease and bandwidth. Yeah, but you know, we may have to come and bother you guys a little bit.
There's one guy that's gonna take like tests. We'll see how it goes, and there's also constants.
Yeah, yeah, I'm sure that he's definitely interested in this. So for the knowledge of it, to figure out what's going to be better. Anyways, I'll let you get to yeah. So last time we worked with some students.
Awesome.
Zoom here.
So I was talking to him.
I like to see like, is it at one point in that the bezel bar and stuff?
Yeah, the bezel and the monitor. Really nice.
Yeah. I'm so surprised they fit a webcam. It's so,
Wow.
yeah, I think those microphones are up here. Yeah. Steering microphones. But
Yeah, maybe we should be on with the XDS instead.
I don't know, man. Your Mac looks like 20 or better. Like, mine still does really well.
No, yeah. And it has 2060 in it, right?
Oh, the graphics card? Oh, it's a 3050. Jesus. Right now.
Oh,
Dr. Turner, we're still going over theory? Do we have anything else to cover on theory, or we?
No, we're done with those lecture notes. We're doing, there's a lecture notes for like mechanics of materials.
Mechanics.
Yeah.
I saw that on the canvas. So, yeah. Mechanics of materials.
yeah. That's what I have. Kind of review. I think we named the rocket Lightning.
Oh, no, it's my messenger. Josh just texted it. It's like, people, no answers today. I think that's month's in chat. She said we offset that.
Yeah.
I should have asked him what this class. The other reason I really like it is like the 4K monitor on this one is really good.
That's better than mine.
This isn't 4K. This is their,
What's that? 21.
What's it?
I mean, 21.
it's a little higher than 1080.
Well, yeah, what?
I think it's like, yeah, 19 to 21 something or whatever.
Oh, that's right. I
But
really have.
yeah, like the lower red screen has that finish, where the other one is OLED 4K.
Everyone's
And
in
it's just
like everything.
kind of rocks that way, and we have to. I'm like,
I saw that.
Oh, yeah, that's right. It helps to swap between the desktop. But yeah, this is like the one annoying thing that I gotta deal with answers for this small thing. Yeah. I messed around with the resolution just to get it. So I just gotta look at it, try it, and then come back and work manually. It's just one hurdle.
Okay, it's 5:30, so let's go ahead and get started today. Good evening, everyone. How's everyone doing today?
Good.
Doing good?
Excellent.
Ready for the long weekend? I know it's every long weekend's always a welcome sight, no matter how early we are in the semester. So that would be good. Okay, and so today we're going to be going over a little bit of review today. And so, you know, I've never done this before in a finite element class, but I thought, you know, it'd be a good idea to review a little bit of the theory behind strength of materials. Okay? Because in a lot of this class, we're going to be looking at things like stresses and strains and things like that. And every other time that I've taught finite elements, I've kind of always just assumed that everyone kind of had perfect understanding of this stuff. But, you know, I think just to kind of make sure that we're all on the same page, I thought it'd be good just to review. Okay? But the real reason I'm doing this is because I wrote these lecture notes for another class. And I thought, you know, might as well kind of double dip and have them for this class as well. Okay. But before I do that, I do want to go over, so I've gotten a lot of questions on the last activity and what's the best way to save your work, especially for those of you guys who are working here on the lab computers. You know, a lot of times, you know, you're going to want to work on your project a little bit and then, you know, maybe go home for the day and then come back and work on it. And so, you know, I've kind of told people to kind of save one way, but I've looked into it a little bit more and I found a better way to save your work. where it can be easily transferred through like a flash drive or Dropbox or things like that. And so that's the first thing I want to go over today. And then after that, we're going to go over these set of lecture notes on strength of materials, right? So before I do that, are there any questions I can answer before we get started?
Yeah, for the activity, do you require us to submit the answers as well?
No, so for the activity, I just need all the screenshots. And so if you can just submit everything as one PDF, and so all the screenshots that I asked for and all the questions, answers to the questions, then that would be the best way. Yeah. Mhm. Okay. Any other questions? Okay. All right. So let me go ahead and share my laptop screen here so that we can see from here. Okay. All right. Okay. And so so here's an ANSYS project that I have open. Okay. And so previously what I've been telling people is to kind of click on the save button here, right? And so what that does is that it saves two things for you, right? And so it saves like an ANSYS file. And so it's called a WBPG file, okay? And then it also saves a folder which has all of your other, your CAD files and your simulation results in there, okay? And so if you're working on the same computer all the time, and so like, let's say that you're running ANSYS on your personal laptop and you're not going to be moving files in between different systems, this is probably the best way and most convenient way for you to save your files because it's, it's much faster to load them in. But if you are going to be switching machines, when you're working on projects, so let's say that you're working here in the computer lab, or maybe you're working on your laptop, you want to bring it to the computer lab, whatever, you're switching machines. I found that the best, or I looked into it today, and the best way to actually save your results is to use this option here called archive. Okay. And so what that'll do is that'll create like almost like a zipped folder, like a compressed folder, which has all of your ANSYS stuff in it. Okay. So let's go ahead and click that. Okay. Or not. Okay. So this is a really old project. So when I tested this on a new project today, it worked. Okay. And so basically when you click that archive button, it's going to create a zipped version of your ANSYS project onto it. Okay. And then it's just going to give you a single file. Right? And so you can take that single file, you can email it to yourself, you can upload it on Dropbox or move it between your flash drives. And then when you want to resume the project, you have to click on this import button right here, okay? And then that when you click on the import button, it'll ask you to select the zipped folder that you created through archive, and then you can load that in on ANSYS, okay? And so this is a little bit more convenient if you're going to be switching machines, because then you just have to worry about just one single file. The only downside is that it can be a little bit slow to load it again because it kind of has to unzip all of your finite element files. But this kind of saves you the trouble of like having to make sure that you save the right folder and that it's in the right place and things like that. Okay? Because I think an error that a lot of people have been getting over the past week is that you save your project using this option right here, okay, and then you try to move the folder into your flash drive. You can try to open it again. And then ANSYS complains that it can't find the file because it's not in the exact same location that it was before, okay? And so to save you that kind of issue, I would recommend to use this archive function, which creates that zip folder, okay? All right, any questions on that?
Does it matter whether you save it on the workbench or save it on the mechanical?
You should save it on the workbench because workbench will save absolutely everything. So, and so if you just save it on mechanical, that just saves your simulation results. But then if you want to save the CAD file and the material properties, then you have to save it from workbench. Good question. Okay. All right. Okay. So I'm going to go ahead and stop sharing here and we'll come back to the lecture notes. Okay. Okay. All right, so the topic for today's lecture is going to be basically a review of strength of materials, okay? And so for you guys, it might be, this might be a little bit more boring for you guys because probably you guys have seen strength of materials a little bit more recently than my graduate students, but I think nonetheless, I think it's always useful to review some of these important concepts because from here on out, I'm going to assume that, we all kind of are really familiar with this. Okay. Okay. And so if you recall from your strength of materials class, the whole idea of the subject of strength of materials is that it basically describes how structures or physical objects deform in response to external forces. Okay. Okay. And this can be anything from like your pencil, like bending your pencil, inwards, to anything like designing like a bridge or a big building. Okay, all those kind of follow the same theory that's outlined in strength of materials. Right, and a big determinant or a big factor in determining how structures deform is the properties of the materials. Okay. Okay, so I think we all kind of intuitively kind of understand that, different materials will respond differently to different kinds of stresses, right? And so if you took like a steel rod and you tried to bend it, okay, unless you're like, Hulk or someone, then you're not really gonna be making much progress on that. But if you took a rod that was made out of, say cheese or something, right, and you try to bend it, it's gonna bend pretty easily, okay? Okay. And so central to strength of materials is this whole idea that stresses are going to develop within these materials. Okay, so let's go over kind of the whole concept of stress. Okay. All right, so we've seen stress already, right? And so we've if you remember from our first activity, one of the results that I asked you guys to do for the first ANSYS activity was to show how the stress is distributed within that plate, right? And so we have basically a plate with a hole, we're stretching it, and then because we're stretching it, stress is going to be developed on the inside, okay? And so let's go over, let's start with just very, very basic. So let's start with just the units for stress. Okay? And so stress is its pure definition is simply just a force that's distributed over an area, okay? Okay, and so its units is exactly that. And so its units are going to be force divided by area. Okay. Okay. This symbol sigma here, this is the general symbol that I use for stress. And I think that's pretty, most people use sigma for stress, and so it's not one of those ambiguous ones. Okay, and so the units for that is going to be force over area. Okay. And if you want to put this in terms of SI units, the most common unit for that is going to be the Newton, which is a unit of force over a meter squared, which is a unit for area. Okay. And this has a special name because it was named after the guy that came up with it, right? So he was the genius that said, let's put force over area and let's name it after me. Okay. And so the SI unit for stress is the Pascal. Okay. And so it's abbreviated as PA. Okay. Right. And so stress, definition-wise is pretty straightforward, but it's also not the only thing out there that has units of force over area, right? Another quantity that you might be familiar with is the whole concept of pressure. And so pressure, if you remember from maybe like a fluids class or something, is also has units of force over area. Okay. So I think, one common question that I get a lot is, what's the difference between stress and pressure, and when do we use both? Okay, because they both, unit wise and both dimension wise are exactly the same thing. Okay. And so, the difference that I usually tell people is that the difference is in context. Okay. And so pressure is usually something that you apply externally to a surface. Okay. My stylus would cooperate. And so think about the boundary condition that we applied on our first ANSYS activity, right? And so to apply that tensile load, we applied it as a pressure, because that's an external force that we're applying onto our structure from the outside. Okay. And so one way that you can remember this is you can think of pressure as something that's applied to you, right? So maybe like your professors are applying pressure to you by forcing you to do assignments and exams, things like that. Okay. And so it's something that's applied externally. On the other hand, stress is something that develops internally to a structure in order for it to maintain equilibrium with its outside. Okay. Okay. And so one way to kind of remember this is you can think that, you develop stress, or you get stressed because of the pressure that's applied to you, right? And so professors apply pressure to make you turn in homeworks, and you get stressed because you want to complete them, right? So that's kind of how to remember the two of them. So even though dimension wise they mean the same thing, they both are just a force over an area. The context in which you talk about them and the context of their application is different. Okay. Okay. Any questions on this so far? Okay. All right. So let's do a simple example to kind of illustrate, just the whole concept of stress. Okay. So you might have seen this example before in a previous class. Okay. And so let's consider a simple rod that's in tension. Okay. Okay. All right, and so we're pulling on the rod on both sides, okay? And so we know that this rod is in static equilibrium because because all the forces are going to cancel out, okay? Okay. And so when I say that this rod is in equilibrium, that means the entire rod is in equilibrium, right? And so that means if we slice this rod, so let's say that we slice it like that, okay? Okay. And so in order for this segment here to be in equilibrium, we also need to have some kind of force that opposes the tension like that, okay? Okay. And this internal force that's needed to maintain equilibrium, we call this the stress, okay? Okay. And so we know that the symbol for stress is sigma, right? Okay. And so just from a simple equilibrium equation, and so if we sum up all the forces here, we set them equal to 0, we can come up with an expression for sigma for this case, okay? And so on the left side, we have the tensile force T, okay? This has to be equal to the stress, okay? Multiplied by the area, right? Because remember, stress is a force divided by an area. And so in order to get force back from it, we have to multiply it by an area, okay? And so this area, this A right here is the cross-sectional area of the rod. Okay. Right, so fairly straightforward. Okay. Okay. And so, we have a situation like this where, we have this straightforward equilibrium, right? But I think a fair question to ask is, let's say that, we have the same kind of cross section here, okay? And we have our applied load T, okay? And so, a fair question to ask is, why don't we just have a T, another T that shows up inside the middle right here, okay? And so why don't we just have, a point force that's there to oppose the load, right? Because in the end, you get the same thing, right? In the end, you get you get a situation which is a static equilibrium because both of those T's cancel out, okay? And so why don't we have this? So why do we have to bother with the stress and multiplying by the area? Okay? And so the reason we don't have this is because whenever you have a structure and it has any kind of cross-sectional area, any forces that it experiences is always going to distribute across the entire material. Because it doesn't make sense where if you have, if you just have a point load T, and you're trying to assign where it is, right? And so if you can imagine that the cross-sectional area is like this, okay? And so I kind of took the rod and I kind of turned it on its side, okay? It doesn't make any sense to apply this T, in any location here, right? And so that doesn't really make sense. And so what makes more sense is to distribute that T over this entire surface, so that it's all balanced, right? And so basically every particle of the material is basically doing its part to sustain an external load, right? And the way that we kind of express that mathematically is through a stress, okay? And so that's why, when you're talking about forces that are internal to a structure, you usually talk about it as stress, because then that encapsulates the fact that, this force is going to be distributed kind of very evenly across the entire material, okay? All right, any questions on this? Okay. All right, so let's go over the different kinds of stresses that you can see, okay? And so there are two different kinds of stresses I want to talk about based on the direction that they act, okay? Okay. And so the first type of stress is a normal stress, which is actually the one that we saw on the previous page. Okay. And so a normal stress is going to act perpendicularly to a surface. Okay. Right. And so if you have a surface that's vertical like this, then the normal stress is going to be acting horizontally to it. Okay. Okay. The other type of stress that we have is a shear stress. Okay. And the shear stress is going to act parallel to the surface. And so stress is actually, a pretty complex state. And so it's not just a single value that that a structure experiences, right? It depends really strongly on the direction as well, right? It depends on whether direction is going to be, parallel or perpendicular to the surface, but it also depends on, the Cartesian directions too. And so it depends on X, Y, Z. And so if I draw kind of the most arbitrary case, okay. So if I draw a cube like this, right? And so this cube could represent kind of a small particle that may be on the inside of your structure, okay? Right, and so this cube is going to experience normal stresses and shear stresses as well, okay? And so the normal stresses I've highlighted in pink right here, okay? And the shear stresses I'll do in blue, okay? And so you can see that all the normal stresses are acting perpendicular to the surface on which it's acting, right? Whereas the shear stresses are going to be parallel to it. Okay. Okay. And so in addition to having two different kinds of stresses, we can also characterize the stresses in terms of which direction that they act. Okay. Right. And so, we have kind of two different kinds of characteristics here. And so we have, normal versus shear, and then we have directions as well. And so in fact, the way that stress is kind of generally described in the structure is through the stress tensor, okay, which accounts for all these different things. So have you guys seen, the concept of the stress tensor before in previous classes? Okay, so you guys have seen it before.
Similar to Moore circle.
Yeah, yeah. People keep saying Moore circle, and it's something that I don't think I ever learned, but I think just by osmosis, I think I understand it a little bit now. Okay, so I'll skip the explanation of all the different components of the stress there, because I think you guys have seen it. But I'll show you what the stress tensor looks like, and then we'll kind of pick up the discussion from there. Okay. Okay. So any questions on this? Okay. All right, so let's talk about the stress tensor then. Just to kind of write it down, just to kind of be on the same page. All right, so the stress tensor, it's a mathematical quantity which represents, all kind of the complex state of stress that can be happen in a structure, right? And so we give it the symbol sigma, okay? And it's a matrix, and so I put a line under it. Okay. And this matrix is a 3 by 3, at least in an arbitrary case for a for a 3-dimensional solid. Okay. All right, and so that's our stress tensor, and we know that there are 6 unique components, right? And so we have this, everything on the diagonal here, those are our normal stresses. And then everything on the off diagonals, these are our shear stresses. Okay. Okay. And one thing that we know about this in particular is that this stress tensor here is symmetric. Okay. And so tau xy is going to be equal to tau yx, tau xz is going to be equal to tau zx, and tau yz is equal to tau zy. Okay. And so in the end here, we only have six unique components, and then the other ones are just kind of mirrored across the diagonal. Okay. Okay. And so in summary, what I want to illustrate to you guys is that stress is complex, right? And so when you're describing stress within a structure, there's lots of different things to account for and lots of different stress components. Okay. Okay. And so let's bring this back to our ANSYS activities, right? And so in our ANSYS activity, what I asked you guys to show was the equivalent stress distribution within the solid, right? And if you remember from the from the activity, when you were looking at the equivalent stress, what you were looking at was kind of like a heat map of where stress was highest or not, right? And so, if you remember, there's a color bar on the outside which kind of shows the what red represents what orange and green and stuff like that. And all that's good. But what I want to highlight to you guys is that when you're viewing those results, when you're viewing like the equivalent stress inside ANSYS, you're only viewing a single number, right? Okay, same for the principal stress too. Okay, maximum principal stress. Okay. Right. And so, if we're only viewing a single stress value inside ANSYS, then I think a fair question to ask is, which stress are we viewing, right? Because we have six here, right? And so are we viewing this one? Are we reviewing this one? Is it going to be sigma ZZ? Is it any of the shear stresses, right? Okay. If we're only viewing a single stress, the question is, which one are we viewing and which one is actually most important for us to see, okay? And so the answer to this is that you're kind of viewing all of them at the same time. Okay. And what I mean by that is that, you can take the 6 different components here and you can kind of put them into a formula to compute just a single stress value from that, okay? And so I'll call this we'll call it like an aggregate stress value. Okay. Right. So there's a formula that ANSYS is using underneath the hood that that incorporates all these different stress components. Okay. And the formula that ANSYS uses for this is called the von Mises condition. Okay. Right. So that's why in ANSYS, when you view the equivalent stress field, it calls it the von Mises stress. And on the next page, I'll write out that formula for you, okay? Just so that it's not a formula that you have to kind of memorize, and it's not anything we're actually going to manually compute ourselves. But it's mostly just for your reference, just to know that when you're viewing equivalent stress inside ANSYS, you know exactly how it's taking into effect the all the different shear components and the and the normal components. Okay. Okay. So any questions on this? Okay. All right. So here's the formula for the von Mises stress. And so we'll call this sigma V. Okay. Okay. And so we take the square root of 1/2 sigma XX minus sigma YY squared. Okay. And so we take the difference of 2 of the normal stress components plus sigma xx minus sigma zz quantity squared, okay, plus sigma yy minus sigma zz quantity squared, okay? And so every combination of the normal stresses, you're going to take the difference and square them, okay? Plus 6 times each of the shear stress components squared. So we have tau xy squared plus tau xz squared plus tau yz squared. Okay, one more parenthesis.
This is all under the same square root. correct?
Yes, yeah. So it's all, everything here is under the square root. And so, you know, I kind of ran out of space, but you know, all of this is under that. And so again, you know, this is not something, you know, it's not something that I'm, you know, you guys need to memorize or anything like that. It's not something we're going to use to compute anything. This is just kind of for your reference, okay? And so when you ask ANSYS to compute equivalent stress, now you know exactly what it's computing for you. Okay. Okay. All right, so that's the von Mises stress. Right. So now the question is, you know, how do we actually use this, right? And so we've looked at the von Mises stress inside our plate, right? It's something we're to continue to look at for the rest of the semester. Okay. And so I think a fair question to ask is, you know, what is this actually used for, or you know, why do we even care about the von Mises stress to begin with? And so the most common way that we're going to use the von Mises stress or the equivalent stress is to determine whether a structure is going to fail or not. Okay. Okay. And so we'll do this in the activity next week, actually. And so, you know, one thing that you can look up for every material is a parameter called the yield strength, the yield stress. Okay. Okay. And what the yield strength is it's a value of stress. Okay. And what it tells you is that if the equivalent stress ever exceeds the yield strength, then the structure is going to fail. Okay. Okay. And so you can think of the yield strength as basically the maximum amount of stress that the structure can withstand before it actually starts to break, okay, and fail. Just clean that up a little bit, okay. Right. And so next week, you know, we're going to do an activity where I'm going to have you guys do a finite element simulation of a bike crank, okay. And so in the bike crank, you know, the bike crank is going to be subjected to a certain amount of load. And I want you guys to determine whether the bike crank is going to fail under those loads. Okay. You know, once you have that information, you can then make some comments on the bike crank's design, right? And so if you determine that the bike crank is going to fail, then what you can do is you can modify the design in order to make it stronger, so it's not going to fail. Okay. Or, you know, if the bike crank is, you know, very far from failing, you know, it's very safe, you know, maybe you can shave away some material from it in order to kind of cut down on the manufacturing costs. Okay. And so that's a little bit of a sneak preview of you know, what we're going to do next week. Okay. All right. Any questions on this? Okay. All right. And so that's stress. Okay. So now let's go over the concept of strain. Strain is the other kind of important quantity for strength of materials that we need to know. Okay. And so the whole idea with strain is that it's a measure of how much a structure is deforming relative to its original configuration. Okay. And so I think the classic example that's given is probably the easiest one to understand is if you have a rod that's fixed to a wall, okay, and this rod has some initial length L, okay, and let's say that you're pulling on it with a tensile load T, okay. In response to that load, the bar is going to get stronger or longer, sorry. Then so let's say that the original length was L, and then in response to the load, it's going to increase in length by an amount delta L, okay. And so the strain in this case is just going to be the change in length L, delta L, divided by L, okay, which is the original length, okay. And so the important thing about strain is that it's unitless, and so it doesn't have any units because we basically have a length divided by the length, right? And so that's always going to have no units, okay? Because remember, it basically represents a relative change, and so whenever you have anything relative, you're kind of taking the ratio of one thing over another thing, so it's always going to be unitless, okay? And so this is an example of strain in kind of a 1D case, but in 3 dimensions, strain is can be a 3D thing, okay? And so the mathematical definition of strain is that you take the displacement, which is u, okay, and then you take a derivative of the displacement in every single direction, okay? Right, and so underneath the hood, this is basically how ANSYS is defining the strain, okay? And this ends up being a matrix as well, or a tensor. Right. And so basically how you understand the stress tensor, the strain tensor, you can understand it to be kind of the same thing because you have basically the derivative of every single displacement component divided by every single Cartesian coordinate. So you end up with a 3x3 matrix, just like stress. Okay. Okay.
So that's the normal derivative, or is it a partial derivative?
It's a partial derivative.
Okay.
Yeah. So the kind of the if you guys have seen index notation before, so the index notation for it would be something like this, where you have different indices. So the u would be given like index I, and then each of the directions would be j, and so you end up with a matrix at the end. Okay. Again, that's kind of just for just for this class is kind of just trivia, because we're not actually going to be ever computing it, but just to kind of show you guys that stress and strain, they're kind of 2 peas in a pot. They kind of are defined in the same way, and they kind of have the same kind of intuition behind them. Okay. Okay. Any questions on strain? Okay. All right. And so stress and strain are very intimately connected inside a material, right? Not only do they have the similar mathematical definitions, but they also have a strong effect on each other too. And actually, you know, the exact relationship between stress and strain is determined by, you know, what type of material do you have. Okay. And so the simplest relationship in between stress and strain is a linear one. Okay. I think it's kind of the first one that everyone learns in their strength of materials class. Okay. And so for linear materials, and so this covers, you know, most of your metals. Most metals are linear because they just because of their molecular structure. Okay. And so for linear materials, you know, we have that the stress is equal to the Young's modulus multiplied by the strain. Okay. So I think we went over this equation on Tuesday. Okay. And this linear relationship is known as Hooke's law. Okay. And so this is kind of the simplest case where stress is just kind of in order to get stress from strain, the only thing you just have to do is multiply by a number. Okay. And that number is the Young's modulus. But you know, it can definitely get a lot more complicated than this, especially when you talk about, you know, like things like composite materials, things like anisotropic materials. You know, one that's becoming a lot more popular nowadays is like 3D printed materials. Okay, and so 3D printed materials, just by the nature of how they're manufactured, they very rarely follow this relationship here. Okay, a lot of times you have to take the printing direction into account when you're modeling those materials, but you know, if you're talking about just a pure metal that's kind of manufactured in a traditional way through like milling or cutting or lathing, you know, this relationship holds pretty well. Okay, and a lot of the problems that we're going to do in this class will be for linear materials, but you know, we will talk about, you know, what you would need to do for different kinds of materials as well. Okay. Okay. So any questions on this? Okay. All right, so let's go over the concepts of principal stress, okay? Because I did ask you guys to look at principal stress for the assignment as well, okay? Okay. And so principal stress, you know, in reality, you know, it's not used all that much for anything practical. And so something like, you know, if you're determining whether your material is going to fail, you know, you're probably going to use the equivalent stress. You're not going to use the principal stress, but it's kind of a neat, I think, theoretical and mathematical construct, I guess you can say, because it kind of puts the state of stress in a really interesting way. Okay. And so let me start off by saying that, you know, for most practical situations, you know, the state of stress in a material is incredibly complex. Okay. And so let me just do a 2D case just to kind of just so you can kind of see what's going on. Okay. Okay. And so even in a 2D case, you know, we can see that we have lots of different stress components, right? So we have all the normal stresses that are acting normal to the surface, but also all the shear stresses that are acting parallel to it as well. Okay. And this is complicated because, you know, if you're considering all the different stress components, there's a lot to keep track here. Okay. Right. So a lot of times, you know, we like to simplify this, and so that, you know, we can examine just, you know, a simplified version of the state of stress. Okay. And so one way to kind of simplify this the situation is to simply perform a rotation. Okay. And so if we rotate it, and we're a little bit smart about how we rotate the state of stress here, is that we can reach a state where there's no longer any shear stresses. Okay. And so the idea here is to take the same kind of patch of material and then just perform kind of a small rotation. And we rotate it in such a way that, all the shear stresses are either going to cancel out or they get added into the normal stresses. Okay. And in the end, we end up with a situation with, just normal stresses. Okay. And in fact, we get a situation here where we can characterize all the different normal stresses here. Okay. And so I'll call the those two sigma 1, and so I'll call that the first principal stress. Okay. And then the ones on the perpendicular faces we'll call sigma 2, which is the secondary principal stress. Okay. Okay. And so this is convenient. And so instead of looking at this really big stress state, we're looking at these ones. Okay. Right? And so now we're describing the stress state in terms of these principal stresses. Okay. And so in 2D, we have 2 principal stresses, but in 3D, we actually have 3. Okay. Okay. And their names are based on what their numerical values are. Okay. And so you have the maximum principal stress, you have the middle principal stress, and the minimum as well. Okay. Right. So what I asked you guys to do in the activity was to find the maximum principal stress. Okay. Which is basically the maximum of the 3 principal stresses that you got from performing this rotation. Okay. And so again, the principal stresses, they're not often used for anything super practical, just because it's kind of a more of a mathematical and theoretical kind of like, and you can even call it a flex, I guess, that you can rotate and get into this weird stress state. But it's kind of a cool thing to look at. Right? Because one interesting thing to do is you can compare a lot of compare the maximum principal stress compared to what you got in the equivalent stress. Okay. Okay. Because remember the whole point of principal stress is that it transforms your stress state into a basically a normal stress, right? And so normal stresses, remember, are going to be either compressive or tensile, okay? And so if you compare the maximum principal stress to the equivalent stress, and you can see that they're kind of similar values, you can say that, the biggest contribution to the equivalent stress here is going to be mostly from compression or tension, okay? But if they're different, then you probably have a big contribution to shear to your equivalent stress, okay? But there's also kind of better ways to determine whether you have shear stresses or normal stresses too. But but this is kind of just so that you guys kind of know what principal stresses are and kind of know how to differentiate it between equivalent stresses. Okay.
Excuse me?
Yeah.
So then this would be great in the activity then. When you're asking for maximum stress, you're asking for the maximum principal stress.
So the maximum stress is going to be the equivalent one, and
okay.
Yeah, so I wanted to show you the principal stress just because it's just to show you that you can compute it within ANSYS. But the one that's practically used often and the one that you use to determine whether material will fail is the equivalent stress.
Okay, so when you're asking for the maximum stress, you're referring to the equivalent stress?
Yes, yeah,
Okay.
yeah. Yeah, so when I say maximum stress, what I mean is what's the absolute maximum stress value that you see in your entire structure. So that's different from the maximum principal stress because if you can imagine in a generic structure, let's say that we have our plate with the hole like this, okay? And we want to find the stress at this point right here, okay? There are three principal stresses here. Okay. And so the three principal stresses are the maximum, the middle, and the minimum. Okay. And so when I say to find the maximum principal stress, that means just, find the distribution of the third principal stress everywhere. But when I say, just maximum stress, just without anything, I mean the maximum equivalent stress and where it is on the structure. Yeah, it's a little bit of word ninja stuff, but it's yeah, it's once you kind of understand kind of the difference between them, it becomes a little bit more clear. All right, any questions on this? Okay. All right, so let's talk about stress strain relationships. Okay. And so we talked about kind of the linear one before. Okay. And so we've seen that, there are materials out there where the stress strain relationship is linear. Right. Okay. And so if you plot the stress strain curve, you know it looks something like that. Okay. And this is the assumption that we'll make for a lot of the ANSYS jobs that we'll run. Okay. And this works really well if your material is linear up until a certain point. Okay. Okay. And so if the deformations inside your finite element simulation are relatively small, then you can make the assumption of a linear material and your results will be pretty reliable. Okay. But once you start getting away from from small deformations, and so if your deformation is starting to get larger, then you have to start taking plasticity into account. Because probably you guys know already that once you kind of get past this linear regime here, once you get past that linear regime, then the stress strain relationship is no longer linear, right? And so there's always a linear portion kind of right next to the origin, but once you reach past a certain threshold, then the stress strain relationship starts to look something like that. Okay. And so this right here is plastic deformation. Okay. And so there's a way to turn this on within ANSYS, okay? Because if you don't turn it on in ANSYS, then ANSYS won't account for it. Okay. And so in ANSYS, there's a toggle or there's a checkbox for large deformations. Okay. Okay. And so if you have a situation where you have large deformations inside your model, you have to make sure that this setting is turned on so that you can actually simulate that. Okay. Because if you don't, what's going to happen is that ANSYS is basically going to assume that this linear relationship will maintain kind of all the way until infinity, right? And so if you kind of draw a dotted line, okay, and so ANSYS is going to assume that this linear relationship is going to continue all the way up here, okay, even though in reality the material was going to reach plastic deformation kind of way before that, okay. And so you need to make sure that if you do have large deformations, that you turn that setting on, and we'll go over this kind of later on in the semester too. Okay. And so a couple questions I think come from this, I think, and they're very fair questions. And so number one, what do I mean by small deformations here, right? Because that's kind of an arbitrary term. That's kind of a vague term. Okay. And so how small is small? Okay. And I think the other question is, if there's a setting for large deformations, why don't we always just turn this on, all the time, right? And so why is there an option? Why is there like a better option, right? And so why are we doing the crappy thing when, you know, the good thing is something we have to turn on manually, right? And so let me start with the first one, right? So what is characterized as a small deformation? And so a small deformation, you know, unfortunately, there's no hard definition for it, and so there's no hard way to say, you know, for someone to look at a structure, say that's a small deformation or that's a large one, because it's kind of very situation specific. But I'll tell you kind of my rule of thumb for this that I think is pretty, you know, I think it gives you a pretty good intuition. Okay. All right. So what I do to determine small deformation is that I look at my geometry. And I look at kind of the scale of the of how big it is. Okay. Okay. And so what I mean by that is that you know, is your model on the order of millimeters? Is it on the order of centimeters or meters? Okay. And so one thing you can do, and ANSYS does a really nice job of this too, is that in ANSYS you can actually look at what's called the bounding box. Okay. Is you know, what the bounding box is going to show you is, you know, if you were to take your geometry and to put it inside a cardboard box, this is the smallest cardboard box that could fit your geometry. Okay. And so let's take our plate with the hole as an example. Okay. And so if you remember when we were catting this up, you know, the length of the plate in this direction was 300 millimeters. Okay. And then the length of the plate in this direction was 200 millimeters. Okay. And so if we consider just like a small, you know, 2D box, which I guess in this case would just be an envelope. Okay. And so the envelope in this case would be 300 millimeters by 200. Okay. This one's straightforward because our geometry is actually a rectangle. But if you have kind of an oblique or kind of an awkward geometry, you know, think of putting it in a cardboard box. Okay. And this is something you can look up. You know, ANSYS kind of automatically computes this for you. Okay. Okay. And so, you know, once you have the bounding box and you kind of get an idea of, you know, the scale of your geometry. You know, what I usually like to do is I take the you know, I take one of these numbers. So usually these numbers are kind of on the same order as you. Okay. So let me take 300 here. Okay. And so what I do is I multiply my biggest dimension here by 0.1. Okay. Okay. Right. And so if you do 0.1 times 300, you get 30 millimeters. Okay. And so, you know, if you get a deformation in your simulation that's higher than 30, okay, any deformation that's higher than 30, I would consider that as a large deformation. Okay.
30 millimeters.
30 millimeters, yes. Okay. And so if you run your simulation and you see that you get, you know, something like 35, 36 millimeters, then I'd say, you know, your deformations are getting pretty big at that point, and you might want to consider turning on large deformations. Okay. All right. And so that's generally my rule of thumb. And so question.
Yeah, so roughly like 10% the largest dimension.
Yeah. Yeah, so that's my own rule of thumb. But you know, kind of everyone else kind of has their own rule of thumb, and as you kind of do more and more of these, you kind of build more intuition for, what looks large and what looks doesn't large. But I'd say as a starting point, I think this is a kind of a pretty good place to start, because, finding out your bounding box is something that's really easy to do in ANSYS. And then just taking 10% of that, I think is really kind of straightforward. And so, if you take 10% of your maximum dimension and you're seeing deformations that are bigger than that, you're probably outside of the linear regime at that point, because it's, then your structure is really kind of deforming a lot. Okay. But of course, 10% is also, that's my own personal number, but some people might have a lower one, like 5%. Some might be like 20% or things like that. Okay. But I think 10% is pretty reasonable, and I think it works well for most materials too. Yes. Yeah. 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 So the biggest dimension works well when all your dimensions here are pretty much the same. So 300 and 200 are pretty close. But if you have a situation where one of your dimensions is much bigger than the other one, I would probably take the smaller dimension for that one. Yeah, so a lot of it is kind of situation specific, and so you kind of have to use your judgment, and you kind of have to see. Also, kind of you can use your eyes too. And so if you look at your structure and it's kind of doing this kind of really wacky thing, probably something went wrong, and you should look at your settings a bit. All right. Any questions on this? Okay. All right. So now let's go over the large deformation setting. Okay. Okay. And so why don't we just always turn this on? Because if we turn it on, then we don't have to worry about, estimating the largest deformation, doing this 0.1 thing, or whatever, right? And so if we can just always turn this on, then, ANSYS is going to know what to do. And so kind of the simplest answer to this question is that, if you're going to do a large deformation simulation, those can get pretty expensive. Okay. And so if you're considering classic deformations, which is from the modeling perspective, we call it a nonlinear type of analysis. Those are much more difficult to actually compute than a linear one, which is a lot cheaper. Okay. And so if you're only doing maybe like one or two simulations of a large deformation, then it's fine. But the way a lot of people use finite elements is that they kind of tinker with their designs and kind of run simulations constantly, right? And so if you can imagine that, if you run a linear simulation, it might take maybe 30 seconds to complete. But if you run a nonlinear one, that time can go up to 3, 4, 5 minutes. And so if you're making kind of constant design changes and you're making a tweak, you're running a simulation and you have to wait 4 or 5 minutes every single time for it to run, that's going to add a ton of time to your analysis in the end. Okay. And so, the large deformation setting is something that you should use, kind of sparingly and kind of, in situations where you're really confident about everything else in your design. Okay. Right, so that's kind of the biggest reason why it's it's not used that often. Okay. The other thing that you might run into is that if you're defining your own material, okay, and so you're setting a custom material property. Okay. And you actually do this quite a lot because ANSYS actually doesn't come with that many materials in its library. Okay. If you are setting your own custom material within ANSYS, you kind of have to supply all of the data and all of the parameters that's needed for plastic deformation as well. Okay.
Professor?
Yep.
If you're transferring a model from SolidWorks into ANSYS and you already set the materials on SolidWorks, will that transfer over too?
Yes, yeah. So that's one nice thing about doing SolidWorks parts is that the material does transfer from SolidWorks to ANSYS. Yeah. But if you're not using SolidWorks or you're using kind of the one of the CAD softwares within ANSYS, then supplying the right material properties is something that you have to do. Yeah. Yeah. So that's one thing you have to be careful of because it's because when you're we won't do this next Thursday, but we will be specifying our own custom material. And what you'll see is that it's kind of very easy to kind of specify just the bare minimum for your material, and then say, I'm done with this. Okay. And so if you don't supply the right parameters for this plastic deformation, then actually, thankfully, ANSYS will actually stop you. So it'll say, you don't have enough data for this. But sometimes those parameters can be a little bit hard to find, especially if you're working with the material that's not standard. And so that could be something that kind of gets into it. All right, any questions on this? Okay, and so there's one last thing I want to go over today, and it's this idea called St. Bernan's principle. I don't know if he was actually a saint. He'd be the patron saint of mechanics, I guess. But it's a really useful principle. Okay, and so the whole idea with St. Bernan's principle is that any kind of local deformation or any kind of local stress within a material, a lot of it depends on how close you are to the actual place where the load is being applied. Okay. And so to kind of sum up St. Bernan's principle in a couple words is that, local effects or local deformations within a material, they're very localized to any kind of external loading that's around them. Okay. Okay. Right. And so external effects would be things like loads or constraints. Okay. And as you move further away from these, from these areas, okay. And so in other words, as you get more interior to your model, you kind of start to lose the effect of those external effects. Okay. Okay. And so let me give you an example here. Okay. Okay. And so St. Bernan's principle is it's not like a mathematical thing, and so there's no formula for you to compute, but it's mostly just to kind of give you some intuition about how materials generally behave when they're exposed to certain conditions. Okay. All right. So this is how I would use St. Bernan's principle, kind of in a general way to kind of help me check my finite element results. Okay. And so here I have a cantilever beam. Okay. And let's say that I'm going to apply a load at the end of the beam, just like that. Okay. Right. And so what I can see here is that there are basically two locations here where we're applying external effects. Okay. we have the left side of the beam, which is where we're constraining the beam, right? And so that's an external effect that we're imposing on the beam. Okay. And on the right side, we have the this is where the load is being applied, right? And so this is another area of the beam which is which is going to be really right next to an external effect. Right? And so even before running a finite element simulation, I can already kind of tell where kind of the areas of interest of the beam are going to be, right? Kind of just based on how close they are to the boundary conditions. Okay. And so for this case, I've run beams a bajillion times, and so I kind of know the answer already. But then what I can tell you from this figure here is that on the left side of the beam where we fixed it, this is where stress is going to be concentrated. Okay. Okay. And so that's kind of one area where we're going to see an interesting solution there. I put interesting in kind of quotes. Okay. And then on the right side of the beam where we're applying the load, okay, this is where deformation is going to be applied. Okay. Okay. And so that's going to be another kind of interesting area in our solution, because that's where a boundary condition is being applied. Okay. And so if you look at the areas where which is farthest away from the boundaries, and so if you look at kind of these areas right here, okay, in the middle of the beam, this is where things are generally not as interesting, right? And so you kind of have not very high deformations there. The stress is going to be kind of low. Okay. And so usually a lot of times, the middle of the beam, or kind of as you get farther away from the boundary conditions, it's not going to be as exciting. Okay. And the reason for that is, is because it's farther away from from where the boundary conditions are applied. It doesn't really feel their effects as much because we have that distance that's separating them. Okay. And so you can use this principle here to kind of gauge and kind of to check your finite element results, because a lot of times you would run a simulation and then you might get something weird where you get maybe you get stress that's concentrated right here. Okay. Okay. Right. And so if you get stress concentration at somewhere that's far away from the boundaries, that's a little bit strange a lot of the times, because it's not something that's it's not something that kind of really makes sense, because you're far away from the constraints and you're far away from the loads. Okay. And so those are kind of situations you might have to look at. Maybe my mesh can be improved a little bit there. Maybe in some settings I'm running are not that good. Okay. And so it's kind of a way just to kind of check your work, that generally as you move away from kind of external loads, external constraints, you kind of feel their effects less, and that effect is reflected in things like the deformation and the stress. Yeah.
When we did the bar lab, we had tension on a bar, we pulled it.
Yeah.
It created necking in the center of the bar, not near the left.
Mm-hmm.
So does that contradict what's going on here?
Yeah, no, it's a good point. And so necking is kind of it's kind of one of those non-linear effects where you kind of the bar is kind of deforming a lot. And so this kind of assumes that you have a linear material where things kind of stay cross-sectional the same. And actually for the activity that we're doing next week, that's also gonna kind of contradict this, because the bike crank I'm going to give you guys has a pretty defined neck, and so that neck has a very small cross-sectional area. So that neck is going to appear right in the middle of the bar, and so you're also going to see a stress concentration there because of that neck. And so this is not like a end-all be-all kind of thing. It's kind of more just a little bit just to kind of build your intuition for certain situations. Yeah.
I saw a question somewhere where it was asking about the stress concentration for this exact situation,
Mm-hmm.
but there were 3 points of interest on the fixed end.
Mm-hmm.
And one of the questions was, where is the highest stress
Mm-hmm.
concentrated located?
Yeah.
And it asked for the top surface, the bottom surface, and in the middle.
Mm-hmm.
What would the answer be to that?
Yeah, so for that particular case, that's kind of more of a beam bending question.
Yeah.
So for this, And so this kind of tells you kind of where the stress would be concentrated.
Yeah.
But to kind of answer your question, so, you know, you kind of have these three points right here, right? And so on top of the beam, this is where you're gonna have your highest tensile stress. And so on the bottom of the beam, you're gonna have the highest compressive stress because you're kind of bending the beam that way. And in the middle, it's gonna basically cancel out right there.
Okay.
But you know, all St. Bernard's principle will tell you is that, you know, on that side of the beam, that's where you're gonna have high stress
Yeah, I
concentration.
just thought it was an interesting question.
Mhm.
And you brought it up.
Oh, yeah. No, yeah, it's definitely one of the interesting applications of that. Mhm. Okay, so any other questions on any of this before we pack up for the week? Okay, all right, so that's all I had planned for today. And so thank you guys for coming. Thank you guys for tuning in. And so enjoy your long weekend, everyone. Stay safe out there. And I'll see you guys next week.
A question regarding the homework.
Yep.
So, the problem asking about us using the maximum stress, I kind of inferred that using the simple stress was the answer I was supposed to use. Would it be wise, well, obviously it would be, for me to change my answer from the principal to the equivalent max stress?
For this activity, I'm not gonna look at it too carefully because it's just the first one, but for the future, when I ask for the maximum stress, I mean the maximum equivalent stress.
Equivalent, not
Yeah.
maximum.
Yeah, it's a lot of time, and so, you know, when I talk about maximum stress, a lot of times you're interested in where that's physically located on your structure. And so a lot of times the location of the maximum equivalent stress is also the same as the maximum location of this location of the maximum principal stress.
Right.
And so a lot of times they correlate together. It's just that the exact value that you compute and you're trying to see if your material is going to fail, you're going to use the equivalent stress for
So the equivalent is basically taking into consideration the entire geometric shape.
Yes.
So the principal focusing on one point.
Exactly.
Okay.
No, he wants the max equivalent. So like, there are a couple of questions that ask all three, but when we only ask for two, like maximum information and maximum stress, go for maximum.
Yeah, I did the same thing.
I did
For this activity, it doesn't matter all too much because it's just the intro one. But for the future, I'll be a bit more clear about it.
Gotta change it.
And then there was a question as well, because I think it was the first one, you put 1,000 megapascals and I think it said 10,000.
Yeah, it's
I kept 1,000.
for this one, you know, it's a typo, so it doesn't really matter. But for the future activities, I'll be more careful. For this one, you know, it's just okay. It's just the intro activity.
Yeah, okay, I was gonna say, I'm already like super far in.
Oh yeah. Don't worry about it.
Thank you.
This guy's so much fun.
You're just separating out rocket.